What? Oh. You guys ready for the test? No. Are you excited for the test? No. I did not give you any tips on the test, right? Apart telling you where's the area covered. Yeah. Yeah, so I also didn't bother. So we will be very neutral, very neutral test. Okay. I would say that the test is hard, but hopefully not too hard. Okay. Let's see how's standard. One advice for you is if you don't if you start on the question, just skip the question first. Okay, and then do the next one. Don't start on a question, right? So if you start on this question, jump to next question first. Okay. And then if you have time, then you come back. So don't start on the question or too. Just keep going, keep going. So I'll give you reading times before the exam. So if you found out any problem with the question paper, then you can raise during the reading time. So the reading time is 10 minutes. After 10 minutes, we will start the 90 minutes exam. Okay. But we will do lecture first before exam. I scared you will be too tired after the. What do you guys have a test yesterday? Right? How was it? Huh? What are this? Huh? Is it doable? Doable. Okay. Actually, I found out you guys ask a lot of good questions, but only during the exam times, right? So if throughout the lectures, you should also ask me the uh, similar question. And then from your question, sometimes I realize that um, maybe you haven't actually understand the statement yet. Okay. So if you don't understand the statement, right, whatever I explain is futile. Okay, there's no use. You don't understand either. Okay. So mostly when you don't understand what I say, right, go back to previous sentence what I mentioned. Okay, what's the statement I mentioned? Do you understand the statement on top? Okay, and then you figure out whether my explanation makes sense or not. Okay. So I will try explain statement more before I give more explanation next time. So I think we are a bit behind the schedule, so maybe we need to rush a little bit. Okay, but saying so, having said so, you still can interrupt me. Okay? Really, just interrupt me anytime. Okay, let's continue the partial derivative business. Okay, so these questions give you a function. Okay, a function from R2 to R, given by u equals to e to the power x sine y. Okay, and then this question asks you to prove that this is a solution of the Laplace equation. Okay, what's the Laplace equation? Okay, is the second derivative of u with respect to x plus the second derivative of u with respect to y equals to 0. So if you want to show this equation here, what you need to get, okay? So clearly from here, you should get the second derivative of your function. Okay, they call it u for now. And then add up together, you get 0. Okay, to satisfy this equation. Everyone clear? Yeah. So let's recall how to do the derivative. Okay. So the first thing we learn is from the formal definition. The formal definition tells you that you need to take a limit of a special function, right? So you need to take 2 points nearby and then take the difference and then divide it by the x coordinate. Okay, but in this case here, we won't use the limit definition. We just apply the usual derivative rule, differentiation rule. Okay, so what we need to compute is the second derivative of u with respect to x and the second derivative of u with respect to y. So when we do partial derivative with respect to one variable, we should keep the other variable constant. Okay, we treat the other variable constant. So for example, if we want to differentiate u, okay, with respect to x, we need to treat our y as a constant. So if y is a constant, then sine y is also a constant. Okay, so ex times sine y become a function in function of ex multiplied by a constant sine y. So what do we get by partial derivative? Differentiate this, we get sine y ex again. Okay, you differentiate ex, you still get ex. If you differentiate this twice, okay, you still get ex times sine y. Okay. Similarly, if you want to differentiate u with respect to y, okay, so you treat y as a variable. Yeah, and then you treat x as a constant. So x is a constant, e to the power x, also another constant. Okay, so if you differentiate sine y, what do you get? You get cos y. Okay, so what you get here is a constant multiplied by cos y. Okay, similarly, if you do the second derivative with respect to y, what do you get? You just get minus e to the power x sine y. Okay, so let's check whether these two sums sum up to 0 or not, right? So you can see clearly that the second derivative of u is ex sine y, and the second derivative of u with respect to y is minus e to the power x sine. So when you add them up, you get 0. Okay, so you satisfy the plus equation. Okay. So this example, I just want you to recall how to do the partial derivative. So next, what's really this partial derivative is doing? Okay. So if you imagine, on the uh, R to R case, okay, function from R to R. Okay. When you get the gradient, what do you have? Let's say at this point you get a gradient. Okay, what do you have? You have a line. Okay, but now on the surface you have two partial derivatives. You have a direction on x, have a direction on y. Okay, so you get two lines, right? So if you take linear combination of these two lines, right, you will get a plane. Okay, so suppose that f has a continuous partial derivative, an equation of tangent plane to the surface, z at the point is just z minus z naught plus equals to the gradient okay, the x gradient times x minus x naught plus the y gradient times y minus y naught. Okay, so the diagram is like this, something like this. Okay, so you can see that on the function from R to R, you got a line. Okay, from a function from plane R2 to R, you get a plane. So you can see that this tangent plane, right, really have the same dimension as our surface. Okay. So let's try an example. Okay, let's try to find a tangent plane to this surface here. Okay, so let's find the tangent plane to this surface at the point 113. So let's look at our new function here. That fxy equals to z, which is equals to 2x squared plus y squared. Okay, so to get the tangent plane, we need two gradients. One is with respect to x, the other is with respect to y. Okay, so with respect to x, what's the partial derivative? We have 4x here, right? Okay, with respect to y, what's the partial derivative? This one, 2y, good, okay. Okay, good. So, in general, the tangent plane equation is what? Let's recall again. If you forget, it's okay, but we will recall here. It's just z minus z naught equals to fx at the point, where is it? Yeah, at the point x naught, y naught, times x minus x naught plus fy x naught, y naught times y minus y naught. Okay. So in this case, what is our x naught, y naught, and z naught? I want to know a guy or a girl, I don't know. Yep, Seng, is it here? Yep, Seng. Oh, okay. So what's our x naught, y naught, z naught in this case? What's the point we're interested in from this question here? Zoom? Oh, you can't see, is it? Okay. Let me know earlier. Can you see now? What's the point we're interested at? That's on the tangent. Huh? Sorry? I can't hear. Can you speak louder? Can you speak louder? It's given. Oh, of course, it's given. That's why I'm asking you what's given. 112. Okay. So we are finding a tangent plane on the 113. Okay. So x naught, y naught, z naught in this case is 113. So we need to plug everything in. Right. So what do we need to compute? So we need to compute what is fx at 1, 1. Okay. So what is fx at 1, 1? It's just 4 times 1, which is 4. And fy at 1, 1 is just 2 times 1, which is 2. Okay. So together we have z minus 3 equals to f 4 times x minus 1 plus 2 times y minus okay, so this is a plane equation. This is a plane equation. So what's this plane doing? Okay. So if you still remember what you learned in the before university about this equation of plane, you should see that uh, this coefficient in front of this vectors here constitute the normal vector of that plane. Okay, so this 4, 2, 1 is a normal vector on the plane. Okay, so for example, this is a plane, so the normal vector is perpendicular to the plane. Okay, it tells you how the plane slanted. Make sense? Sorry. On -1. Okay. 4, 2, -1, you mean? Yeah, right. You are right. Okay. 4, 2, -1. We will visit this again before the vector calculus. So what are we doing here? Okay. So what's the graph of z equals to 2x squared plus y squared? So it is an elliptic parabola, which is this one, paraboloid. Okay. Paraboloid. And then the tangent plane we find is the bottom tangent plane. It's really a plane. It's not a curved plane. Okay, it's really a flat plane. Okay, so if you zoom in more into that point, okay, into the point 11113. Okay, if you zoom in further, okay, you can see that our surface coincide with the plane. Okay, if you zoom in further and further. Okay. This is similar to the case of one function of one variable. Okay. So for example, you have a tangent line on a curve, right? So if you zoom in the curve more and more, right? So it is really a straight line. So it locally is the same as the surface. Okay. By the way, right, for my exam, right, you don't cram too much. Otherwise, you will get distracted. Because my exam is testing on your ability to use the formula. Yeah, I just want to like give you a reminder. Okay. Yeah. Don't cram too much. Keep your mind alive a bit. Okay, don't be too dead. Otherwise you will stuck there. You get what I mean? Yeah. Don't cram too much. Okay. Yeah. Just now I told them, yeah. Because you come late, just now I told them. I give them tips. So if you when you reach the question that you don't know how to do, right? Don't stop there. Just keep going. And then if you have more time, you come back. Huh? And then okay, very good. Yeah, very good. No, I mean you come back and do later. I doesn't mean that you skip then you just put nothing, right? You come back if you got more time, right? Okay. Yeah. Okay. Okay. So what we are trying to say is the derivative form a linearization, okay, of the surface. Okay, what's this linearization here, right? Okay. So what are the components in the linearization? Okay, you have a point, okay, you are interested in, and then you have an equation of plane. Okay, so the whole thing form a linear map, linear plane. Okay, so what does this linear plane do? Okay, this linear plane provide a approximation to your fxy. Okay, so why we say so? Okay, let's look at the picture here. Okay, let's look at a picture here. So, what do we call as a linearization? Okay, so this tangent line here is what we call the linearization of the function. Okay, so you can try and think that your function or your curve, your line is curved. Okay, the function is a curved line, but the tangent is a linear line. Okay, so you think of like you stretch the curve, okay, the straight line. So they coincide at the point where you evaluate the differential, okay, or the gradient. But at the other point, okay, you can see that with some adjustment, you still can get your real fx. Okay, this is called the linear approximation to your fx1. Okay, so for example, what? So let me give you an example, right? Let me give you an example. So let's use our favorite x squared y equals to x squared curve. Okay, let's say we want to find the gradient at the point 0, 8. Okay, so let me ask one person who. Okay, ask Ellie. Ellie, right? Is it Ellie? Okay. So what's the gradient at A, 0, A for y equals to x squared? So, okay, actually x squared plus 2 shifted already. So what's the gradient at 0, A? Huh? What's the gradient? Sure. So what's the gradient at 0, A? Huh? What? No. I want to evaluate at 0, A. 2x depends on x, right? So my question is, huh? 2x 0? What's 2x 0? 2x evaluated at the point 0, A. What do you get? Huh? Did you understand my question? A little bit confused. Okay, good. So first you differentiate, right? Differentiate. So what's 2x? 2x is the gradient at every point. Yeah. But I want the point at uh, when x equals 0. What do you get? 0. Okay. So you get 0. So what's this? Okay, you differentiate with respect to x, and then you get 0. Okay, this is a horizontal line. Okay, so horizontal line, what's this gradient here? What's the gradient line here? So this is the x, no, y. Okay, y equals to 0 times x minus, sorry. So if I follow that formula, right, what should I get? I should get x y minus a times 0 times x minus 0, which I get y equals to a, which is this horizontal line. Okay, is that okay? So this 0 here is the derivative with respect to x at that point. Okay, so this 0 and this 0 is the same. So let me point out this 2 0 here is the same. Okay. Okay, so y equals to a. This is one of the example. So you can see that. What can you see? What can you see? So at this curve here, right? So when f x equals 0, you get a. Okay, but for this point here, you also get a. Right? For the point on tangent line, you also get a when x equals 0. Right? But when x equals to 1, okay, what do you get on this fx? You get 1 plus a. 1 plus a. Right? You evaluate your function at x equals to 1. Is that right? Okay. But at your tangent point and your tangent line, you get what? You get just a. Okay. So there are some difference there. But here just says that this is approximate. Okay. How? So as a mathematician, right? So you want to ask how close they are. Okay. can we measure the distance or not? Right. So in this case, can you measure the distance? What's the distance? Huh? What's the distance between this 1 plus A and 1A? What's the distance between them? 1. Okay, the distance is 1. Okay, so that means if I plus 1 to this approximation here, they are actually equal. Okay, so I can go from this tangent line here and then reach my curve just by plus 1. Okay, so you can see that it really depends on point, right? If it's further away from this 0 A point, you need to add more values, right? Depend on x. So it is a function that depend on x. Okay, so this is a one variable case. Hey, this one, I mean, this concept is really important. If you want to jump my example, it's okay, but this concept is very important because when you go to higher dimensional case, right, you can't easily imagine this. Okay, you can really do this in the low dimension. You can really see it clearly in low dimensional case. Okay, so you really need to understand this. So what I want to say is the tangent plane or the tangent line, okay, depend on what dimension you live in. You can approximate your original surface. Okay, depend on where your points lies. You need to add a respective how to say the what's that? You need to add. You need to add what? What's the word? Suddenly I'm stuck. So you need to add the uh So you see the tangent plane and the curve, right? They agree on the point. Okay, they agree on the point where we take the derivative. But away from the point, they are a little bit they are different. Okay, because our surface is curved. Okay, at every point the tangent is different. Okay, but we can estimate the point on our curve using the tangent line or tangent plane. Okay, so depend on what x you take or depend on what point you take in the domain, you need to add a respectively the right amount to compensate. Okay, to compensate the difference. Compensate the difference. Make sense? Okay. So for example, just now I give you an example at x equals to 1. On the curve, you get 1 plus a, but on the plane, you get a. Okay, so the compensation here is 1. Okay, you need to add 1 to your tangent plane so that you can get back to your. Okay, so if you add the right compensation, you can imagine that you are applying a transformation here. Right? So uh, you are like matching the tangent line to the surface. Okay. 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 So let's go to the higher dimensional case. So for example, this blue piece here is your surface. It's a curved surface. And then you found a tangent plane on AB. Okay. ABFAB. So you also can imagine that if you add the right number compensation to your plane, you can revive your um, original surface. Okay, so this is what we have here. So what we are doing is we will say that f is differentiable if the following is true. So what's this huge thing here? All right, what's the huge thing here about? So let's go through what's everything is here first. Then later we'll say more. So what's this? So this says that if f is differentiable at AB, so you need to start with a AB point, okay? And then look at the function. Okay, so let me draw some picture. So let's have an AB on XY plane. And then you look at the surface here, right? So what kind of surface you want? Maybe draw a sphere here. Okay. So you look at this point maybe, and just look at this point here. You look at this A, B, F, A, B. Okay. So what do we mean by differentiable? We mean that it is differentiable if we evaluate the point around FAB. Okay. So we look at A with some distance away from A and with some distance away from B. Okay, let's look at around maybe somewhere around the ball AB. Okay, and then we look at F of it. Okay, we look at F of it. So maybe somewhere here. Okay, F of the ball. Everyone see it? Need to go bigger. Just let me know if you want me to zoom it. Okay. So you look at F of it. Okay. And then we'll say that this is differentiable if what? If this value of F is equal to the value of FAB, okay, the original point, plus a little bit of the gradient times the difference in X, plus the gradient times the change in Y, plus a small change in X, plus a small change in Y, then we will say that this uh, dif differ this function is differentiable, okay, as the change going to 0, okay, the epsilon also go to 0. A bit complicated, is it? Is it a bit complicated? A bit dry here. A bit dry. For our a bit dry. Let's see. Okay, so let's see how we get this equation here, right? Okay, let's see how we get this equation here. So previously, what do we have? Okay, we have this thing here. Okay, just now we conclude that we can approximate our curve, our surface, or our function using the linear approximation. Okay, so differentiability tells you that how you can do this estimation here. Okay. Okay. So how we get this equation here? So you really can take x and y. Sorry, let's do bigger. X and y to be a plus delta x and b plus delta y. Okay. So if you take x equals to a plus delta x, and then y equals to b plus delta y. Okay. What do you get in this term here is just delta x. And then you get, similarly for y minus b, you get delta y. Okay. If the function is differentiable, this tells you that what to add. Okay, it's exactly epsilon times delta x plus epsilon times delta y. Okay, these two epsilon might not be the same. Might not be the same. Okay. And moreover, if you go closer, and closer to AB, right? Okay, this equation here will be true also when true for taking epsilon 1 and epsilon 2 to 0. Okay. So you can see that when these go to 0, right, it is just a plane on the at the point AB. Okay. 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 So what I want you to get here is we can estimate our surface using the tangent plane. Okay, we can estimate the surface using the tangent plane. So a differentiable function is one for which the linear approximation is a good approximation when xy is near AB. In other words, the tangent plane approximates the graph f well near the point of tangency. Okay? So it is what we said just now when you zoom in and zoom in and zoom in, right? It is just that plane. Okay? So for example, our Earth is also a differentiable manifold. Okay, differentiable function, differentiable surface. Okay, so you see when you zoom in, and zoom in, so you are in the zoom in version, right? So on this plane here, do you walk like this or not? Do you walk curvedly? No, right? You walk like a plane. I mean, you walk on the Earth as if you are walking on a plane. Okay, but if you see the Earth from outside, it is a sphere, right? Okay. Yeah. Okay. 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 So next, so there's a theorem here. Okay. So in principle, if you want to check differentiability at AB, you need to check this. You need to check the limit here. Okay. When delta x delta y go to 0, this epsilon and epsilon 2 have to go to 0. But let's say you know how to compute the partial derivative. Okay. You know how to compute fx and fy. Okay. If they exist at the point AB, okay, moreover, they are continuous, then f is differentiable. Okay, so you can use this theorem here to check whether a function is differentiable or not. You just need to check two things. Okay, the partial derivative with respect to x and y are exist, and moreover, they are continuous. Okay, so we will use this instead of the original definition. So in this course, right, you will always see that we introduce a very complicated definition, but immediately we introduce a tool for you to use. Okay. But if you go to a later course, right, you have to prove everything from the definition. Okay. Usually we don't have so much nice property anymore because we are dealing with more general stuff in future. Okay. But for this course, we will always deal with nice object. Okay. For example, if we deal with nice object that have partial derivative and partial derivative with respect to x and y exist, and then continuous, then it implies that that original f is differentiable. Okay. Continuity of partial derivative implies differentiable of the function of two variables. Okay, let's apply this. Okay, so we will see one example here. So show that this function is differentiable at 1, 0, and then find its linearization there. Okay. Okay, so from the theorem just now, to show that this is differentiable, we just need to find the partial derivative of f with respect to x and y. Okay. And then show that it is continuous around that point. So fx, what is fx? Fx is just e to the power xy plus xy times e to the power xy. Okay. So what is fy? Okay. So you need to keep x constant and differentiate with respect to y. So you get x squared times e to the power xy. Okay. So does this two function exist near 1, 0? Okay. So these two functions are composite of continuous function. So they are continuous. Okay, so in particular, they also exist near 1, 0. Okay, so fx and fy are defined around 1, 0. Okay, and also continuous. Okay, and continuous at the particular point 1, 0. Okay, because they are composite of since fx and fy are composite of continuous function. Okay, So by theorem just now, we haven't proved it. If you are interested, you can prove it. By theorem just now, we know that f is differentiable at 1, 0. Okay. Differentiable at 1, 0. Okay. So next we want to find the linearization. So what's the linearization again? Okay. So the linearization is the what? Is the tangent plane. Okay. Is the tangent plane. So let's write down the formula for linearization. Okay. If you cannot recall, never mind. We will just recall here. So what's the linearization? Is the point, okay, is a plane, okay, first of all, it's a plane. It's a plane with two, how to say, is the plane that is the linear combination of two vector, okay, two vector. What's the vector? So first you have the gradient with respect to x, okay, and multiply by xa, and then plus the gradient with respect to y times y minus b plus a shift of AB. Okay, you shift the plane to FAB. So note that this plane, right, is the swoop out version of our tangent line. Okay, for tangent line, we only have one of them, right? But for plane, we have two. Okay, one is the x direction, one is the y direction. Okay. Okay. So what we need to compute here? So what's our AB in this case? So we want to find a linearization at 1, 0 because it is differentiable there. Okay. So at AB equals to 1, 0. Okay, what do we have? So F 1, 0, we have 1 times e to the power 1 times 0. Okay, which is just just 1. And then we need to compute what is fx at 1, 0, which is e to the 0 plus 1 times 0 as well. And then e to 1 times 0, which is just 1. And then fy at 1, 0 is 1 squared e to the 1 times 0, which is just 1 again. Okay, so we got all 1. So what's our plane here? Our plane here is Lxy equals to 1 plus 1 times x minus 1 plus 1 times y minus 0, which is x plus 1. Okay, so the normal vector here is 1, 1 minus 1. Okay, so the picture here is this. Okay, so you can see that this curved plane is our z. Do we call it z? Yeah, call it fxy. Okay, so this is our fxy. Okay, fxy. Okay, so where is 1, 0? So 1, 0 is in the middle here, right? So here is 1, 0. 1, 0 is in the middle here. And then you cut out a tangent plane there. Okay, so you can see that this tangent plane cut through our surface. So at different point, right, you need to do a different compensation. Okay, one of them you need to decrease it. One of them you need to increase it. Okay, okay, depend on where you are, you need to do a different compensation. Okay, but if you zoom in more and more and more and more and more towards the 1, 0, you will really see this tangent plane. Okay. Hopefully. Yeah. If it is differentiable, then definitely you will see it. If it's not, then maybe. Okay. Okay, next, we'll go through this chain rule question. So why we need chain rule? So let's say our differentiable function xy, right, is described using another variable called t. Okay, so let's write down. So we have our two variable function, okay, fxy, and then we write our x and y in terms of t again. Then we need to do chain rule here. Okay, when you want to differentiate with respect to x or y. So how do we do it? What's the formula here? So when we want to differentiate z with respect to t, okay, because you already expressed everything in terms of t, then it's the same as you differentiate f with respect to x, multiply by differentiating x with respect to t, and then plus, okay, so it's a plus here, differentiating f with respect to y, multiply by differentiating y with respect to t. Okay, so this is a higher dimensional chain rule here. So in short, it is like this. So last time, Zhou asked about, can I write partial as d? Okay, so here show you the difference between partial and d here. Okay, so if you use del on z, if you use del, right, it means that this z here contains a variable other than x. Okay, but when you use d here, this x is really depend on t. Okay, yeah, okay. So yeah, so that's why they introduced this notation here for you to differentiate. Okay, so there's one easy way to memorize this. Okay, there's one mnemonic to memorize. So what you can do is you can write down what's your function first, okay, or your variable. So z you can write in terms of x and y, okay, and then x is with respect to t, y is also with respect to t, okay. On the edges, we can write down the partial derivative. For example, if you go down the line from z to x, okay, so you can put a differential z with respect to x, partial differential. And then when you go down from x to y, you can put a dx dt. And then similarly on z to y, you can put partial z with respect to partial y. And then from y to t, you have differentiate y with respect to t. Okay, so why is this good to memorize? So if you want to differentiate z with respect to t, okay, so you need to go down this path here. Okay, so when you go down the path, you multiply the differential together. Okay, if you go down the other path, differentiate with respect to t, you need to multiply these two together. But these two paths both belongs to differentiate z with respect to t. So you need to add the two paths together. Yeah, you can memorize it using this tree diagram. Later it will be getting more useful when x, y is in terms of another two variable. Okay, so now it's just in terms of one variable. Then later we'll see we can express x and y in terms of two variable again. So we will have another branches coming out. Okay, so this is later we'll use it again. So let's see how we use this tree here. Okay, let's see how we use this tree here. So for example, we have this z equals to s cubed times y. Okay, but x is also in terms of t. X is equal to 2t and y is equal to t squared. Okay, so how? We want to find z with respect to t. I think one easy method you can imagine. What's the one easy method you can imagine? Can you see one easy way to do it? I don't want you to just follow the method. So what's the easiest way to do it for this question? Sum x equals to 2t and y equals to t squared, right? Because this is given. So what you get is 2t cubed plus t squared times t squared, which is just 8 to the power t over 5. Okay, now this become a function of one variable in t. So now you can just straight away do dz over dt, which you get 40, 40 times t to the power 4. Okay, so this is one easy way. Okay, so this should be the first thing you should think about. Okay, because this question is easy. But for hard question, then you need to use our method here. Okay, let's see how this method apply here, right? So the formula is if you want to differentiate z with respect to t, okay, but this z is defined using two variable, and then that two variable are defined using a common variable. So we need to use a chain rule. Okay, so what's the way to memorize it? So if you have this, so you need to write down this tree diagram here. Okay, so first of all, z is defined by two variable x and y. Okay, x and y respectively are defined by t. Okay, so along these edges, you can put in the differential. Okay, from top to bottom. So you differentiate z with respect to x, and then differentiate x with respect to t. Okay, so both line here belongs to differentiating z with respect to t. So we need to add these two branches together. Okay. So along the first branch, you will have del z over del x times dx over dt. Okay, so this is the first branch. The second branch is del z over del y times dx dy over dt. Okay. So what is differentiating z with respect to x? Okay. So this is just 3x squared times y times dx over dt is what? 2. Good. So del z over del y is s cubed. dy over dt is 2t. Okay, good. So how? There are x, y, t in the same expression. Okay. So we also can do the substitution here. Okay. So we get 3 times 2t squared times t squared times 2 plus 2t cubed times 2t. What do we get? We get 6, 12 t to the power 4 plus 8, 16, 16, 412, 16, 16. Let me see. Okay, so here wrong. So here is 4. 4 times 8 is 4 times, okay. So 3 times 4 times 2. So we get 24 plus 16, 3 cubed, which is 40 kilo. So this is kilo. Okay, so a bit convoluted, okay, a bit overkill, but this method will be useful for harder question. Okay, when you can't do straight substitution. Okay, let's skip this application question. I will provide so you can try out. It's 2:50. So let's continue. I think we got time. Okay, let's do until 3 o'clock, and then 3 to 10, 3:10 we break, and then 3:10 to 3:20. Yeah, done. Okay. Yeah, we're going up. Okay, so let's skip what? Skip. Should we skip? So this is a tree variable. Okay, so this is tree variable. So let's just discuss what formula we use here. Okay, So this is a 3-variable case. So we have a W. Okay. W, what kind of variable contains in W? Y, and Z. Okay. And then this X, Y, and Z defined in terms of what variable? Huh? Wait for me. I finally know who is who you. Okay. Okay. So okay. So W in terms of X, Y, Z, right? Okay. So what's the variable? What's this X, Y, Z defined on theta? Okay. So three of them are all in theta. Okay. So the difference here we have is the extra Z here. Okay. So the difference here is we have an extra Z. So what you can do also, you put on the edges what differential you have. So going from top to bottom, okay, going to top to bottom. Okay, if you like, I put an arrow here for you to remember. Okay, top to bottom, you can put the differential. So here you got W connecting X, so you have dW over dx. Okay, so since W have more variable than X, right? We will put a del notation here. Okay. Okay. For X to theta, we will put differential X with respect to d theta. Similarly, you will do for W to Y, which is partial derivative of W with respect to Y, and then Y to theta, you get dy over d theta. W to Z, you get del W over del Z. And then Z to theta, we get dz over d theta. Okay. So if we want to differentiate dw versus to d theta, what do? We just add up all the branches. Okay. Along the branches, we multiply. Okay. Different branches, we just add them together. Okay. So all together, we have del w over del x times dx d theta plus del w over del y dy d theta plus dw over dz times dz d theta. Okay. Yeah. So more variable, you still also do the same. So is there any problem if I put dw over d instead of del w over del theta? Is there any problem here? Is there any problem putting dw over d theta instead of del w over del theta? Any problem here? Huh? Why? Okay, because the w can be written as a function of just only theta. Okay, this is what we do just now, right? Okay, if we know how to express x and y in terms of t, then we can write everything in terms of t. Okay, then we just differentiate. Okay. Okay, 5 more minutes. Let's go to the next one first. Okay, so this is the second chain rule. Okay, the second chain rule here has what I mentioned just now. Your x is in terms of two variable, okay, two variable, and then your y is also in terms of two variable, okay, x and t. Both of them are x and t. So what do? Then your z can be written as st. Okay, so two variable again. So what we are doing here is first you have z equals to function in x, y. Okay, then your x, y is a function of xt. Okay, So you could imagine that when we write down this equality, right? Equality here, right? So you can see that when z equals to something in terms of xy, and then you can see that here xy gets substituted by something in xt. Okay. So instead of differentiating z with respect to xy, you can differentiate z with respect to s and t. Okay. So now we put back the del here again, right? Because our function is newly expressed in terms of s and t. So there are two variables. Okay, so we use del here. Make sense? Make sense or not? Okay. Okay, maybe I ask one person from the back. Sheldon. Okay, so why we put del z over del x? Huh? So say again. Say again. Before because of the function. Okay, z function is what? Is what? Is delta? What's delta? What is the delta? Huh? The d? Z. Wait, what are you saying? So you said z is the delta. Ah, what delta? Okay, I'm asking why we are putting del on z when we differentiate z with respect to x. This is my question. Why we put del z over del x instead of dz over dx? Huh? The function is what? Huh? The function is what? I can't hear, sorry. Is z. What is z? And I put mn or pq or not? Okay, so what's z? Y. Okay, so z equals to fsy. So why? There's no x, there's no s here, right? So how I can differentiate this function with respect to s? There's only x and y. How? Is this a constant function or what in s? No. Why? See, this function is with respect to x and y. Why you differentiate with respect to s? Because x also is a function in s and t. Okay, sure. You still haven't answered me why we put del instead of d. Okay, now we have function in terms of s now. So why we put del instead of d? Don't know. Okay, so because in this function we have more than one variable. We have s and t. Okay, if we just differentiate with respect to one variable, we need to put them. Okay, make sense? Does it make sense? Okay, if you have two variables but you only differentiate with respect to one variable, you need to put them instead of d. Okay, if you when you put d, that means there's only one variable inside there. You just differentiate with respect to that variable. Okay, make sense? Yeah. Okay, so let's stop here, and then we take a break until 3:10. Okay, and then we'll come back. Before 3:10, okay, we will need to set up the exam. Right. So if you are ready, right, can you move all your belonging to the front? Yeah, move all your belonging to the front. Only left with your cheat sheet and your stationery. Yeah, move all your bag to the front. And please sit as fast as possible from each other. Yeah. Yeah, I will. So sit at least one free space from each other. At least one. I think we should have it now. Please bring your cheat sheet together with you. And we used to bring cheat sheet for exam. So cheat sheet is like different people have different. Huh? Final, I think so. Hopefully, yeah. Okay, please move. If you can move earlier, then we'll start earlier. Okay, Zhixian, can you stick to that table? Yeah. Should be fine. Should be fine. Okay. Okay. So as usual, usual exam rule holds. Please don't cheat. If you cheat, then you will fail the exam. And so I need some help. So all the paper required, I think, is enough. Should be enough. If it is not enough, there's like the other page is empty, so you can write on it if you want. Okay, I will provide draft paper as well. Okay, I think should have enough space. It won't have enough space if you keep writing and cancelling, writing and cancelling. Okay, so please write your actual answer inside here. So once you got it, fill your ID and name, okay? And then you can start reading. Okay, we will have reading times until 3:20. Okay. So I need some help. So can Ming Xiu, what Wai Ying? Okay, Ming Xiu and Wai Ying. So one of you distribute the draft paper, one of you distribute the test paper, and then I want both of you to count. Okay, but don't tell each other how you count. Yeah. So you count inside your heart. Both of you have to count how many students. Okay. And then you let me know. So one of you get the question paper and then the other of you distribute a draft paper. Draft paper. Yeah. And then both of you have to help me count how many of them. Okay, once you got it, you can start read. You can write your ID, the ID and name. If you found any problem with the question, you should raise the problem between this time. But don't answer yet. Not right. Don't answer yet. But in case if you really need more paper during the exam, you just raise up your hand and then I will get some for you. So this paper is only one-sided printed. So if you want to write more, you can write on the other side of the paper. And you can read it now, but don't do yet. Just read the question. Okay.
The confirm with him.
Mhm. You can read. You can go back. You don't count yourself.
Spotify so Spotify 我跟他手上有两个
2个 is these two.
these two 然后
Okay.
我找两个 draft 对
Okay, okay.
so
Yes. The clock is that.
Yeah.
Okay, I will put a big clock on the wall. Okay, I will put the clock on the wall later during the test. Okay, so you read first. I distribute another paper to another person. But don't start yet. You can read first. If you have any problem, you just raise hand. I'll come to your place. Yeah. Yeah. What do you mean by this one? This one? This one? Oh, you mean you write it here? You can start now. You can start now. 15 minutes left. Do you all need more times? Huh? Okay, another 10 minutes. finish. I give you 5 minutes to clean up your solution, check your name, check your student ID. After 5 minutes, we'll collect. Clean up your solution, check your name, check your student ID. And I want you to submit your cheat sheet as well. Write your name down because at least I found 2% is not using written form. So write down your name, how to collect. I'll see what action need to take. Stop writing. So write down your name in front of the exam paper, also the cheat sheet. Write down your name. And remain on your seat. Pass it to the front. I want the draft paper, exam paper, and the cheat sheet separate. And just pass down the lane you sit in. Separate your draft paper and the cheat sheet and your exam paper. You'll count the right number before you. Yeah, please keep please keep waiting for the collecting the paper. What happened to this one? Exam paper, draft paper, and patient, everything separate them, please. Please separate the exam paper, cheat sheet, and draft paper. Yeah, can you hear me also? Hey, this one. Nine. Seven. How's it? Done. How to separate the draft and cheat sheet? Done. Talk. Done. Everything correct? All eight. Huh? What? Nine? Someone wrote two. What's the name? Who is the name? You. Okay, write your name first. I'll see what happened. Three people wrote the name. Remember you forever. Drop. Hey.
Huh? We'll see after marking.
Correct. Eight. Okay. Yeah, everything top. You get nine. You get eight. This one get eight. This one nine, right? I counted this one. This is nine. Nine. This is nine. This is nine. This is nine. Okay. So is it hard? Yes. Okay. We will see what happened after marking. Maybe we'll do adjustment. We'll see. Okay. So thank you for your participation.
没有时间做，做不完了。啊？谢谢我们吗？谢谢，不用客气。
我今年他跟他关我已经
差不多。看一下谁做的是。
应该他跟他关啊，他跟他关我 approximation 做不出，这是我整个不会
没有时间做。啊？
啊，这个
Part one 哦。你先做到上面先。
有第五题，
换了很多，高调是吧？
有第五题，他不懂有第五题，
我在拍。
不是我放可是，
都没有读题目。
也不够。
那有可以拿回来啊？
什么东西可以拿？
哎，那个